Okay, so let's get started. First of all, a gentle reminder on quiz tomorrow. Okay, so come prepared. Uh, so this week we'll sort of conclude linear algebra. But before that, let's look at a few. Let's do a quick recap on what we did in the last class. So we started by looking at different ways of defining inner product in a finite dimensional space, right? So V transpose U is not the only way by which you can, or V Hermitian U is not the only way by which you can define inner product, right? There are other ways. So one way was basically you look at U Hermitian Q V, where Q is a positive definite matrix. Then this also mimics the inner product. Therefore, this is a new inner product. So the moment you keep on changing Q, you'll get different class of inner products. And this induces a class of norms also, right? And then we saw what do you mean by a unit ball or an epsilon ball with respect to a norm, right? For example, if you look at 2 norm, the epsilon ball would be basically all points at a radius r from the origin, right? That's very clear. But if you use a different norm, instead of 2 norm, let's say you use a q norm, it turns out that the ball is not really physically the ball, but it'll be an ellipsoid, right? In 2 dimension, it's an ellipse, right? Yeah, so later on, we looked at a few other things. For example, how do you find the eigenvalues and eigenvectors, right? We came up with an algorithm. So what is the algorithm? You randomly pick a u, you take AU, normalize it, you get u1. You take AU1, normalize it, you get u2. AU2, normalize it, keep on doing that, right? It will converge, right? So the u1, u2, u3, the sequence will converge to the some vector. So that vector is called, it will be an eigenvector corresponding to the maximum eigenvalue. So what do you do after that? You randomly pick an pick a vector orthogonal to that. Keep doing that, right? Each time when you update, for example, a u2, when you update a, let's say u1 dash, u2 dash, and so on, you should not forget to project it onto orthogonal subspace of u1, or the eigenvector corresponding to the maximum eigenvalue, right? So then we started looking at the operator norms, right? So what do you mean by an operator norm? Of course, if you are given an operator, for example, a matrix, I don't know how to define the norm of that. Of course, I know one way is Frobenius norm, right? We saw that. The other way is you convert that matrix into a vector, right? How do you do that? Well, you can stack one below the other. That gives me, and take the norm, that gives me the Frobenius norm. Or you operate it, you take x and operate, you take a and operate x. You get ax, which is a vector. Look at the norm of that and normalize by x. Because if you don't normalize, what will happen? If I pick a vector x whose length is really, really large, then the norm will also be typically large, right? And we verified the fact that this is indeed a norm. This is called, what norm is called? It's called operator norm. Okay, there are other names to it. It's also called soup norm. Okay, these are there are a couple of names for this. Okay, then we looked at the eigenvalue decomposition, and I think that's where we kind of stopped. Okay, so let's look at okay. Okay, so today we will continue with that and sort of try to conclude. If not today, maybe on Thursday we will sort of conclude on linear algebra and move on to optimization. Okay.